Okay, so in this case, we're going to look at question 5, and the concept here is find the Norton's equivalent with respect to the terminals AB. So here perhaps they're saying find the Norton's equivalent circuit. So Norton's equivalent circuit with respect to the terminals AB of the circuit seen in the figure. Okay, they have circuit there, so perhaps no need for this one here. Okay, respect to the terminals AB. Okay, so what happens here? So since the terminals AB are here, so notice that they are putting the 5.6 kilo ohms between. So in other words, we're going to take this as the load resistor. So our load is going to be that 5.6 kilo ohms. So what we have to do now is copy the circuit so that we can start following the steps for Norton's theorem here. Okay, so this is the circuit that we have. We want to find the Norton's equivalent viewed from the terminals AB. So in Norton's theorem, what do we need? So if you recall, Norton's equivalent circuit, we want to reduce a circuit so that we have a Norton's equivalent current source connected parallel to a Norton's equivalent resistance, I Norton. And then this will be parallel to the terminals AB. So the load resistor will be connected to AB. So the goal then is to find I Norton, and that's why I wrote I Norton. This is the Norton's equivalent resistance, R Norton. So you have to see that the steps for finding R Norton, they're equivalent to the steps that we use for finding R Thevenin. So these two are going to be equal. It's this that is going to be different. Now, how do we find R Norton and I Norton for a circuit like this one? Well, in the first step, you can start first by finding the I Norton. But in an event that you can't find I Norton, you can still find V Norton first, as in V Thevenin first. So depending on which one is faster or which one is easier. So how does it look like? So get this circuit, we'll copy it exactly the way it is. And then we'll demonstrate two things here. You see, in the first step, you have to open, so we'll remove the load resistor. We know it's connected between A and B, but we'll remove it. So the load resistor is out. Now what we'll do is, we'll show you two cases. In one case, you find I Norton. In the other case, you're finding V Thevenin. So here also remove the load resistor. Now what happens here is, you have to short. If you short the load resistor, so you know the load was connected there. Basically, I can say it was connected between A and B. If you short these 2 points and you try to find the current passing through the short, what you're going for is the I short circuit, the short circuit current. This short circuit current is actually equal to I Norton. And then in the other approach, you open the load and leave it open. So in this case, the load resistor has been removed from the circuit, and then we've left those two terminals open. So in this approach, what you'll be finding is the V open circuit. So the open circuit voltage. This will be equal to V Thevenin. So these two methods are going to be okay. You can find either I Norton or V Thevenin, because you know to say the two are connected from Ohm's law. You can say V Thevenin is equal to I Norton times, you can say R Norton or R Thevenin, because these R Norton and R Thevenin are the same. So this is the connection between V Thevenin and I Norton. So depending on which one you can find first, you can still connect them using this relationship. So it now just becomes a matter of which one do you feel is easier to get? Is it easy for you to get the current that will pass through this line when you short these 2 points? Or maybe it will be easier for you to get the voltage difference between point A and point B in the absence of a resistor there. In fact, if it is easy for you to get I Norton and also V Thevenin the way it is, you might as well just find both for the two circuits. And then instead of going to find R Thevenin, if you have V Thevenin and I Norton, you can easily use them here to get what R Thevenin is going to be. Or instead of R Thevenin, you can say to get what R Norton is going to be. And then you will have your circuit figured out. So let's start with the first circuit. Let's find I Norton. Okay, so here we are. So in this approach, we are trying to find the I short circuit or the I Norton. So in this case, this is just a current that will be passing through the points A and B. So try to look at the circuit and try to analyze this. Which approach is going to be best to find the current that is going to pass through this line? All the methods that you have looked at from Kirchhoff's laws, Kirchhoff's laws, KVL and KCL, from normal circuit analysis, superpositioning, mesh analysis, Thevenin, and so on. Everything is fair game here. Which approach is going to be best suited and easiest to get the current passing in that branch? So when it comes to mesh analysis here, how does it work? So here, of course, I'm saying we're going to use mesh analysis here. It's going to be best suited. And in mesh analysis, we have to just define the mesh currents here. So we can say in this line, we have mesh current I1. In this branch, not in this loop, we're going to say we have mesh current I2. Then finally, we have on top there, we're going to say we have mesh current I3. So let's start with what is happening in each line. So when you're not very sure about what is happening inside a mesh, so here, let's define polarity, positive, negative. So for this one, we can say anything really. So I can say positive here, negative here, doesn't really matter. So when you define what is happening at a branch, you can start first by finding the branch currents and then relate them later on. Like for example, if I am looking at the current here passing through the 2 kilo ohm resistor, let me label this as I1. That's the branch current, specifically in the branch. And then I can also talk about the current passing through the 2 kilo ohm resistor there. So let's say we have, first we have the 2 kilo ohm, the vertical one, and its branch current I1. So for this one, we'll see how it goes. Then we have I'm only going for the shared ones. Then we have the 2 kilo ohms here. And then let's say the current passing through this one, let's label it as I2. Now look at what is happening here. So here you have the mesh current going this way. This is I1. And then you have the mesh current going this way. This is I2. So how does mesh current, the two mesh currents relate to the branch current? So here you have to see that I1 will be equal to, so which of the two is in the same direction with I1? So passing through the 2 kilo ohm resistor, you have to see that I1 is also going downwards. So they have the same polarity. So this is going to be plus I1. But I2 is in the opposite direction. So because of that, I'll say minus I2. So this is how these are going to relate. When it comes to this side here, that one is affected by which mesh currents? So I see that from the loop on top, we have I3 going this way. From the loop down, we have I2 going that way. So when it comes to my I2, my branch current I2, which of the two mesh currents is in the same direction as this one? So you have to see that I3 is in the same direction as that branch current, since they are both going to the left. So I'll say I3 will be the positive one. Then I2 is in the opposite direction to that branch. So I'll say minus I2. So these are the relationships that are there. Now, when it comes to now getting the evaluating Kirchhoff's voltage law for the respective meshes, what do you do? First, the easiest one is perhaps I3. Why am I saying it is easy? I3, you have a current source, dependent current source, but it is at the edge. It's not shared. So this is going to be the easiest. What is happening there? You see, in this branch, the one at the top, what you have is a mesh current that is going in this direction. That is mesh current I3. But according to the branch itself, the current in this line is given as 0.2 I delta. So what does it mean? It now means that this side, and notice that they're in the same direction. So the current in this branch is 0.2 delta, and the current in this, according to the mesh, it's I3. And they are the only two in the same direction. So you can conclude that this mesh current I3 is actually the same as 0.2 I delta. Notice that this analysis here, it's similar to what we are doing here, but the only difference is that here there were two mesh currents which were related. Even here, there were two mesh currents which were affecting the branch. Had it only been one mesh current affecting the branch, let's say the one on top was not there. Notice that I2, these two, the mesh current and the branch current, would have ended up with, okay, the mesh current I2. Notice that mesh current is going to the right, branch current is going to the left. They would have been related, all right, but they would have been in opposite direction. So I would have put a minus there. So this is how it would have been if we only had one mesh active there. Okay, so from here, we have seen that by looking at mesh I3 there, the one on top, automatically we come up with a conclusion that I3 will be equals to 0.2 I delta. Now let's go to mesh 1. In mesh 1, what are we seeing? So there we're going to use Kirchhoff's voltage law. So we first find minus the supply voltage, which is negative first, 280 volts. Then plus, so you find the 2 kilo ohm, and for the 2 kilo ohm, when you look at it, you're finding it positive first. The current passing through it is I delta, but in terms of the mesh current, it is mesh current I1. So you can choose to first go with I delta times the resistance, but you'll soon see that I delta, it's only the same as I1. I hope you're seeing it as well, because it's that 2 kilo ohm resistor. The current passing through it is I delta, and the mesh through it, only one mesh is passing through it, it is I1. Based on this, they are in the same direction, so they'll be equal. So this is why for that one, it's going to be resistance times current. It's going to be 2 kilo ohms. Now that's kilo, so I want to use the ohms. So 2000, and then the current there, mesh current I1. By the time we reach down here for this one, the resistance there, first we're finding it positive. First we're going to have plus. The resistance there, 2000. The current passing in it, it's branch current I1. But remember what branch current is equal to. Branch current is equals to this. So instead of writing branch current I1, I will put I1 minus I2. So I'm basically representing the branch current in terms of the mesh current. And that is the last one because we passed through this, passed through this, passed through this. We are back here. So we are done looping there. So this is what will be equals to 0. So now we're just going to simplify this expression. The 280 goes to the right, becomes positive. We now have 2000 I1 plus 2000 I1 again, then minus 2000 I2 is equals to 280. These become 4000 I1, then minus 2000 I2 is equals to 280. You can drop a 0, 200 I2 is equals to 28. Then we can hold it here. Now we go to the second mesh there, the one at the bottom. For the one at the bottom, when we start, so here we'll start looping from here. First, we find this negative first. So you have to be very careful here. I think this is where you're saying that it kind of confuses in terms of the negative and so on. Here, all I'll do is, if I find an element at its negative sign first, after assigning polarity, I'll take it as minus. And then the voltage there will be what? Voltage is current times resistance. The current passing in this resistor, it's I1. Not the mesh current, branch current first. The resistance there is 2000. And then when I proceed, here also I am finding minus first. So I'll have minus 2000 again. The branch current here, okay, I didn't label it. I think when I was doing it here, this is the one I labeled as I2. It was this one here. This one here. So I'll say small I2. And then that's the last one in this branch, in this mesh. So this has to be equals to 0. Now from there, in mesh analysis, you don't want to use branch currents. You want to use mesh currents. I1 small I and I2 small, these are branch currents. But remember how they relate to the mesh currents. The mesh currents are I1 small I is equals to mesh current 1 minus mesh current 2. And then the branch current I2 will be equal to, in terms of meshes, we presented it here, mesh current 3 minus mesh current 2. So in fact, we could have directly come up with this equation in terms of the mesh currents instead. So if I did that, I would have had minus 2000 multiplying, since that is I1, it would be mesh current 1 minus mesh current 2 minus 2000 multiplying mesh current 3 minus mesh current 2. So I could have gone directly to this version. We see that the 2000 can, actually negative 2000 can divide out, so that we now have mesh current 1 minus mesh current 2 plus I3 minus I2. That is when you divide 2000, negative 2000 throughout. So that now we have I1 minus I2 plus I3 minus I2 is equals to 0. So that here, I2 will add up I1 minus 2I2 plus I3 is equals to 0. So here, after coming up with this expression, let's make a few reductions. Remember, we did come up with a relationship between an expression for I3. We said I3 was equals to 0.2 I delta. So instead of I3, we'll put 0.2 I delta. So this reduces to this plus 0.2 I delta. But don't really want to work with I delta. Is it possible for us to eliminate I delta? Well, guess what? It is. We saw earlier that from mesh 1, I delta was the same as I1. Where do we see that? We saw that here. I delta is the current passing through the 2 kilo ohm resistor here. So the current passing through this is what comes out as I delta. But because the current passing here is only affected by mesh 1, so it now implies that the branch current there is actually the same as the mesh current. So I delta is equals to mesh current I1. Based on that, this expression can now reduce to I1. And then while we have I delta, we'll now put I mesh current I1. This and this can now add up. We now have 1.2 I1 minus 2 I2 is equals to 0. From here, finally, we can say I1 is equals to 2 I2 over 1.2. Then we can get this and put it in equation 1. So when we substitute in equation 1, where we have I1, so we'll put that's 2 I2 over 1.2. So this is going to be, we can say we get 666.7 I2 minus 200 I2, which is equals to 28. From here, we can subtract less 200. This is going to be 466.7 I2 is equals to 28. And finally, I2 will be equals to 28 divided by 466.7. That's 0.05999, so 0.06 amps. So of course, presented in milliamps, this can be 1, 2, 3, so I can say this is 60 milliamps, whichever is comfortable. Okay. From here we have I2. If we want, we can also get I1, but our goal, what was our goal? Our goal was to get the I short circuit, the current that was passing through AB. But you have to see that the I short circuit here will actually be the same as the mesh current I2. And guess what? They'll even be in the same direction, because through this branch, through this line, mesh current I2 will be going downwards, so they have the same direction. So mesh current I2 will be the same as the I short circuit. So by finding mesh current I2 here, we have actually found what our I short circuit will be. So I short circuit, which is the same as I Norton, is the same as mesh current I2, which is equals to 0.06 amps. So just like that, we have found I short circuit. Okay, so now that we have found what I Norton is, which is 0.06 amps, we are now going to move on to find our R Norton. So I Norton we now have. So we now need to find the resistance, R Norton. But when there's a dependent source in play, well, this one here, it would be difficult for us to directly find the R Norton. So instead, we'll take advantage of this expression. So instead of finding R Thevenin or R Norton directly, since we already have I Norton, what we'll do is we'll first find V Thevenin and then take advantage of this equation to find what R Norton is going to be. So this approach is usually deployed when you have a dependent source as part of the circuit. That is when you want to take this route. In the absence of a dependent source, you might want to just go directly and find the resistance. Okay, so let's go right ahead and find the V Thevenin. So to find the V Thevenin, we've already removed the load, so we have to find the V open circuit. So how do we find the V open circuit? So basically it's just a voltage difference. So we have those 2 points. I might as well just remove this and then just look at the voltage difference between this point and this point. So we can go at it in this way. So what will be the voltage difference between the 2 points? So to find the voltage difference, how do we approach it? What you see here is that this tends to behave as if it is an independent circuit on its own. What do I mean? You have to see that the current that passes through this line going upwards, that will be the same current that will be coming this way. Yeah, so the current in this loop will be the same. So the 0.2 I delta comes from this current source, and it's the one that comes to pass through here. So the voltage drop across the 2 kilo ohms can be calculated. So the voltage across the 2 kilo ohms can be calculated by multiplying the current that will pass through there, which is I delta, multiplying the resistance there, which is 2000 ohms. So that in the end, this will just be 400 I delta. Okay, so we have found the voltage drop across the 2 kilo ohm resistor down there. But what is the significance here? You have to recall one thing here. You see, when this source, since we are saying that the current here is basically closed up in a loop like that, there is no current that comes from this second loop that actually gets to continue to go this way. No current gets to flow there. That loop will be closed in terms of current in that line. All the current that comes as I delta gets to go down this way and finally gets to come back this way. So this side, we actually get to know how much voltage was supplied by that source, because the voltage which was supplied by that source was all used up by this resistor. So from this source, the voltage supplied, that's the voltage that will come to pass through point A. So, and that voltage is only used up when we pass through that 2 kilo ohm resistor. In other words, based solely on the current source, this 0.2 I delta, the voltage that it is feeding to this node is equivalent to how much this resistor used up. Since this resistor used up this much, to this node, the 0.2 I delta is contributing, so I can say VA will be equal to, just based on this source, it is contributing 400 I delta much of voltage. But is it the only contributor? No. You see, this power source is also contributing to what the voltage at that node is. Now, remember I said there is no leakage of current to go this side, but doesn't mean that the potential at this point does not affect what is happening there. It also will affect. So let's first find how much voltage will be present at this node due to the voltage source here. To understand that, since we say there is no leakage of current, it implies that this circuit will behave as if it's just a series connection. So it will behave something like this. And then we have a 280 volt source here. Our goal is to get the voltage at this point. The current passing here is I delta. So how much voltage passes at that point? Let me label that voltage as VC. So to get the voltage that passes there, you have to see that it's the same as the voltage that will be used up by the 2000 ohms down here. Now, because these two resistors are the same, so voltage division, they will share the voltage equally, but you can still use voltage division. VC will be equal to the same resistor, meaning this one, 2000 on top by voltage division, over the sum of the two resistors, which is 2000 plus 2000, then multiplying the voltage they are sharing, which is 280. Here you're going to have 2000 over 4000 times 280 volts. Then finally, this is just half of 280, which is 140 volts. So this is how much voltage will be dropped by this resistor here. And hence, it will be how much voltage will be at this point. Now, the voltage at this point will also be felt at this point. It won't be disturbed by how much is happening here. The voltage here will be supplied by that current source. So even how much will be present here due to this source will also have an effect of what is happening here. So VA will be affected by the current source plus the voltage source down there. And just because of the voltage source, we have just seen that the voltage VA will be 140 volts. The only thing that is now missing here is I delta. So what will be I delta? I delta, we're seeing it is coming from here. So let's find what that current there would be. So if you look at this circuit, to get the current passing there, we're going to use V is equals to IR. Here I will be I delta, and R will be the total resistance. V is the supply voltage, 280. I delta here. Total resistance will be 2000 since they're in series plus 2000. So that now I delta will be equal to 280 divided by the sum there, which is 4000. So we have 0.07. Okay, so with I delta figured out, we can now get this expression for VA. Here VA is being calculated as the voltage due to the current supply there, and the voltage due to the voltage supply, how much they are contributing to that node. So that in the end, VA will be equal to 400 multiplying 0.07 plus 140. So the best thing is to avoid, in case you have decimals here, you can actually look at it as I delta, we had it as a fraction. You can just look at it as 400 multiplying 280 over 4,000. You can still look at it that way, in case you had decimals there. So what will be the final solution? Here we get 168 as our VA. So what does this imply? The voltage, the potential at VA at this point is 168. This is at the bottom, so we'll take it as the ground, that is V0. So the voltage difference, which is our V open circuit, V Thevenin, which is equals to the V open circuit, it's going to be the difference between VA minus VB. But VA has come out as 168. VB is the ground, which is 0. So I can take our open circuit voltage as 168 volts. So remember the formula, V Thevenin is equal to I Norton. Here you can use R Norton or R Thevenin. They are still the same thing. So here I'll go with R Norton since that's what I want to find. So V Thevenin, we saw that was 168. I Norton, we got 0.06. So here we have 0.06. So from here, we can now say R Norton will be equals to 168 divided by 0.06. So we get 2,800 ohms, or 2.8 kilo ohms. So we now have R Norton and I Norton. So therefore, we can conclude our Thevenin's equivalent circuit, not Thevenin, Norton's equivalent circuit, will have a Norton's equivalent current connected in parallel with a resistor. So this is point B and this is point A. Our resistor, Thevenin Norton's equivalent resistance, 2.8 kilo ohms. Our I Norton, 0.06 amps. And then our load resistor from the problem, the one we opened, that was a 5.6 kilo ohms. So 5.6 kilo ohms. So this becomes our solution. This becomes the Norton's equivalent circuit.